Firstly, I would like very happy to announce our first speaker, Professor Ho. And Professor Ho received his PhD degree in robotics from Ritsumeikan University, Kyoto, Japan. In 2012, he completed the GSPS postdoctoral fellowship in 2013 before he joining Advanced Research Center Mitsubishi Electronic Corporation Japan. From 2015 to 2017, he worked as assistant professor with Yukodo University, where he led a lab on soft haptics. From 2017, he joined the Japan Advanced Institute of Science and Technology for setting up a lab on soft robotics. His current research interests are soft robotics, soft haptic interaction, tactile sensing, grasping manipulation, bio-inspired robots. He was the recipient of 2019 IEEE Nagoya Chapter of Young Researcher Award, Best Paper Finalist at IEEE SII 2016 and IEEE RoboSoft 2020. So welcome, Professor Ho, and the next stage is yours, please.
Okay, so can you hear me?
Yes.
Okay. So first, I would like to thank Chance and other organizers for giving me the privilege to have the first talk today. Because in your very workshop, we are promised to be very interesting. So as Professor Hatch introduced at the first stage, so dexterous manipulation has been researched for years, right? And there is so many topics that need to be tackled. And I believe one group cannot solve all the solution. So that's why we need to gather and discuss in some kind of interdisciplinary fields, so that we can have a deeper to the current challenge, and so that we can find a solution for that. So my talk today will be about the morphological design of the robotic hand for handling wet and fragile objects. So when I first received the invitation from Chan, so I'm a bit confused about what should I present, because I'm also work on the tactile perception, tactile servoing, which that's why I know Chance for a long time, because we share the same interest on the tactile servoing. But then I believe the mechanical engineering and right now emerging philosophy at the soft robotics, so can be a good basis for designing some mechanical mechanics for the manipulation of the objects. For example, the wet or fragile objects, which is also difficult even for human, right? Okay, so Chance, should I have 30 minutes or?
Yes, 20? So you have 25 minutes for talk and okay. 5 minutes for questions.
Okay, I will try to set the time here. Okay. All right, so a bit introduction about my laboratory. So it's about the soft haptics lab. So we work on the science and technology of the soft robotics, tactile perception, manipulation, and so on. So we can see here some research on the biomimetic side that we try to imitate some good and very interesting point from the nature, such as we and then apply using some soft actuators to implement some tasks. For example, we have some kind of underwater eel-like robots, and we also develop some drones with the deformable propellers, so that you can see. So when the when the propeller crash collision, so it will not drop to the floor, right? And also we have some high 3D printing, so that we can print in very random surface to create some soft mechanism that we want. Of course, on the soft haptics, soft robotic hands, I will introduce later. And also working very much long time in the tactile skin. and tactile perception. For example, we create some multi-modality fabric sensor like this. We can detect the touch and also the proximity. So, and recently we developed some fusion-based sensing for the large scale, like the whole arm or whole body tactile skin, as you can see here. So this is what we are currently doing now. And so today, my focus will be on the morphological design of the robotic hands. So as you can see here. So relating to for designing of robotic hand, right? So you can see, so up to now, there's so many designs, which is not only efficient, but also really interesting in terms of mechanical ideologies. So here, so in our laboratory, so we try to base on the softness and then apply the morphological design. So when you're talking about the morphology, so it should be related to geometrical shape, the shape, and also the measurement, right? But also when you dealing with the materials, you need to care about the I'll say mechanical properties like Young modulus, softness, Poisson ratio, and so on. But so one more point that we also focus on is the tribology, which focus on the interface, contact interface between the objects and the hand. So based on this ideology, we try to, so our aim to reduce the energy consumption in grasping, accommodation uncertainties without doing so much learning approach. And also we want to generate a pleasant grip to the objects, and also using less resource perception as possible. And so, and finally, hopefully we can accomplish some grabs with simple control regimes. So first, I will take a little time talking about the geometry and the material. So how we use the morphology to design a robotic hand, and then I will focus on the tribology with the grasping of wet objects. So actually, so even before the emerge of soft robotics, so me and my previous professor, previous supervisors, Professor Hirai and his group are working quite much on the how we can utilize the softness and also the shape of the fingertip to handling the objects. So here we apply to the like a hemispherical fingertip like this. So what is special about this one? So you can look into the simulation done by one of my previous colleagues in Hirai lab. So so you can see here, even you have only one DOF finger, right? But with the softness and also the round shape of the fingertip, you can actually you can change the posture of the grasp objects without any difficult effort, right? So so here in this research, we try to create some kind of tactile sensing by using the very small MEM scale sensor like this. And this can detect the texture, slippage, and also the contact force as well. So, we also apply some kind of mechanical phenomenon into design of the finger hand. For example, the pre-stretch. So I believe you already heard about that. So the idea is if you have a soft substrate and you have a quite stiff film, right? And so before attach one to each other, if you give a pre-stress for the substrate, so so after you attach to the film, you can create some kind of curvatures like this. So if you apply the external force to this tip, So actually, there will be some store energy will react to that, right? So if you can have some kind of morphological design for this structure, so you can, so hopefully you can create some kind of fingers like this. And then so if you have an object in between, you don't need to give any kind of energy. So because the store energy will be converted to the grip force, right? So that you can grip the object without any kind of consume energy. And the other one is, so here in this case, so we can see here we use the ideology of the morphological design so that we can choose the curvatures of the fingertips by varying some material properties and on the geometry properties like this. So during one setup, you can expect to create some kind of human finger-like shape for that with a different curvature along the finger, and also the different level of store energy into this one. So based on this one, we create some robot hand with some soft finger with the pre-store energies like this. So we use the tendon and pulley to only open and close, open and release the fingertips. So you can see that if you look into the consume energy like this, so you only consume the energy when you open and also release the finger. So once the object is within the fingers, you can see that you can manipulate without any further consume energies like that. And because the finger is soft and not so much constrained, so you can expect to grasp a wide range of objects like this. So we also try to give it with some kind of tactile sensing by using our developed fabric sensor like this. So so without using so much learning approach, so we can actually discriminate what kind of foot objects that that the robot grabs basing on measurement and the capacitance generated through the fabric sensor like this. So with this simple design, right, you can see that you can actually save the energy for the grasping, but also increase the dexterity of the grasp ability of the fingers like that. So another kind of attempt is what I call is grasping by wrapping, right? So if you imagine that it's something similar to caging in grasping, but it's more than that, because if you actually can wrap whole entirely the object, so you can expect to increase the graspability of your finger, of your hand, right? So here is the design idea is also quite simple. So this is something similar to the pre-stress that you see before, but instead of attach entirely the film and the pre-stress substrate like in the previous one. So in this case, you only attach two ends, right? And when you release it, so the film will make it like a curved shape like this. And so imagine if you put the object within the region created by the film and the substrate like that, and then and when you pull very slightly, so you can grasp the objects like this. So we also test the morphology of the film, of the curve film like this, based on the width of the hand like that. And you can and I found that so we found that the length, the height of the curve shape is actually quite proportional to the width of the hand. So so you can imagine that. So if you can control the width of the hand, right? So you can actually change the grasp region of the hands. So we use a very simple opinion for this one. So you can use one motor, and then you can create the quite smoothly the shape of the film like that. Of course, you can use another kind of actuation for this one, but this is the case. And so you can see that if the object go in between, so you can simple simply grabs the object without so much complicated control and algorithm. And even you have one or more, 2 or 3 objects, if you fall into this reason, so you can grasp the object, right? So this is how the hand can grasp like a variety of the objects without so much attempt of control. And also, we also try to give some kind of sensing to this for this hand by using the fabric sensor like this. And so we can find that so the initial phase, the pre-grabs and grabs phase, and quite different one to each other. So we can actually discriminate the many phases of grabs by using the measurement of the capacitance of the fabric sensor. So for example, we have many kind of fragile objects like this, but based on the measurement of the capacitance, so we can grasp quite safely the objects like this. So this is also about the some examples showing how we use the geometry and the materials for designing some kind of novel robotic hand for saving the consumption and also increase simplicity. So next, I will talk about the tribology, which is I think is very important for understanding the contact interface between the hand and also the object, right? So this is actually it's a very detailed but interesting summary of the tribology between two objects like this. So you can see that when you grab some objects like that, so it's not only about the grip force and not only about the friction. Actually, at the micro and the macro scale of the contact interface, there's so many phenomena happen there. For example, you can expect some kind of mechanical loss, of course, but also thermal and also electrical phenomena happen there. So what I interested in these tribologies phenomena is like, and I think it's important for grasping is actually within this red square here. So you can see adhesion, friction, wetting, right, and lubrication. It's actually very important. And if you can control by somehow, right, these phenomena for the robotic hand and the objects, so you can expect to enhance the graspability of your hand, of your the robotic hand. So regarding to that, so that we have some examples in the literatures. For example, we have the Gecko hand, right? That can use that has many brittle on the surface, so to increase the contact and the adhesion, so that it can grasp the very heavy objects. But this is only applied for the dry condition, right? Another case is this is about the like a suction cup, but they try to pump the water into the surface so that the air will not be leaked. So that's case. The lubrication here is actually helping to, this suction to grip the objects even with many convex and concave or like many hole on that. So simply like that. So for suction cups, it's very efficient. The other case is electro adhesion, right? So that you can apply the very high voltage. You actually can grip the objects without so much applied force. But here you have to use very high voltage, which is not always preferable. And this is our another case research for the friction modulation between the grabs objects and also the hand. So by changing the shape of the shape and also the inner pressure of the finger like this. So here, well, I have quite motivation in manipulating the wet objects or the object in the wet condition, because if you consider about some normal case of our daily life and also medical and industry, so you can see that there's many scenarios you have to deal with the wet objects like food, or when you use and you have to go inside the human body with blood or something like that, and also some industrial phase that deal with the wet adhesion, and also for the human care. So So let's take a look a bit about the wet adhesions. So when the wet adhesion will appear, right? It's when you have the two when the contact between the two substrate, and we have the very thin water film inside that. So usually, in the wet adhesion force, it can be estimated by the Laplace force caused by the some shape or curvature or the contact angle, this one, and also the Laplace pressure inside, right? And also we have the force caused by the surface tensions, and also the viscosity force caused by the liquid film here between the and of course it can cause the adhesion both in normal and tangential case like this. But if you have a very flat one, right? If you have very flat case, so you only have one film. But if you look into the tree frog finger toes like this, they actually have many groups like this. So when you have many groups like that, so you can expect that the number of capillary action would increase. So it's something like this, right? So when you have more capillary actions, so you can expect more adhesion force like that. So that's why instead of very flat objects surface, so if you divide into many tiny cells with many groups, right? Many channel like this, if you see here. So actually you can increase the adhesion force. So this is some kind of, so based on that, we design some interface like this. So for example, it's in a 6 by 6 millimeter. So we have the surface with the 3,600 cells, and we have the very small group or channel like that. So with the depth of the 44 micrometer, and also the width is about 15 micrometer. And also the design of the width and the height is very important as well. So and one more thing is that if you make your interface is soft, so and if you have a preload like this, so they actually the also chain the wet adhesion based on what we estimate here. So it's quite complicated, but you can look into our paper. But just one conclusion is that when you attach and you apply the preloads, so actually the wet adhesion force also changes as well. So this is how we fabricate the micro parts and parts for the wet object manipulation, as you can see here. So first we have to make the mold, right? So by using the electron beam lithography, as you can see here, so you can make a mold, and then after that you can pour the silicone into that, and then after that you can create a part with the micro structures on this one. Of course, you can change the size, the shape as well based on what you design. But so basically here we use some square shape like this. Okay, so and also you can see this is how if you look into the microscope, we have some very nice group channel cells, as you can see here. So we actually try to evaluate if the force actually increase when you introduce the micro pattern using the experiment setup like this. So roughly we can conclude that so with the micro pattern part, so the normal force can increase is largest to 1.2 to like mostly 2 folds compared to the normal part like this. And so also the conclusion is also applicable for the tangential force, but the ratio is a bit smaller. And also if you change the preloads, which is like a squeeze force, so actually the generated force also changes as well. And also the tangential force, as you can see here, for the micro pattern part, is much more than the normal part like this. So we have the application for grasping the wet or fragile objects, as you can see here. So first is for the handling of the contact lens, right? So in Japan, so a lot of people use the contact lens to attach to the eyes, but of course for some disabled people, it's very difficult to grasp to take the lens from the case and attach to the eyes. So we think, okay, maybe we can show some kind of potential case for that. By using the micro pattern part for grip the lens in the case, which is inside the liquid, and attached to the eyes, because maybe the finger is shaped soft, so maybe also safe for human. Okay, so we do some kind of analytical to calculate the deformation of the film and also of the thin shell, and this is how we modeling the adhesion in different scenario. For example, shell inside the liquid, outside, and the substrates as well. Okay, so this is a example. So you can see here. This is the hand that we developed. It's very simple, right? So here, so it's a scenario when the objects grabs. So as you can see here, after grab, so even you release, right? But it's still attached to the finger. And so this is how when you attach the substrate. And of course, after that is also how you can remove the contact lens safely from the substrates like that. And another kind of application that we think of is how to create some stable grasping of the wet and deformable objects. So imagine you have you want to grasp a tofu from the sauce like this. So even for human, right, this is very difficult. So what if you can apply that to this case for using a robotic hand but very low squeezing force? Okay, so here is how we try to deal with this problem. So we try to calculate how much force it can apply to grip the tofu, and also how much the tofu deform, and compare between the micro pattern part and also the normal part, right? Okay, so this is a normal part without any structures, and this is a micro pattern part, right? This is similar to what you've seen before. Okay, so this is how we try to modeling it, but because no much time, so you can look into our paper in IROS last year. So to see, the conclusion is that with the micro pattern, so it's actually increase the grasp force, right? Of course, with the adhesion inside, and actually reduce the preload, and also the ratio of strain applied to the tofu one. Okay, so so this is how we have the evaluation experiment. So here is okay. So this case is grabs the object with the normal part, and this is grabs the object with the microstructure part, right? And here is how we evaluate the grasping pressure and also the normal preload. And you can see that you can reduce quite much the load, the grip force applied to the tofu when you use a micro pattern part. And also we try to measure the deformation of the tofu before and after the experiment, right? And you can see here, so this the blue one is the result by the microstructure part, and you can see how we can reduce quite significantly. Okay, so this is the video that you can take a look. Okay, so we actually use with a different kind of okay, sorry, start from here. So this is how we measure the force. Okay. Right. So here's actually the inner pressure, and this is a microstructure part, and this is a normal part. So you can see here's the inner pressure for gripping the objects in this case is smaller than the normal part. And we also test with some case when the objects is inside the liquid, such as this is in the sauce, soy sauce, right? And you can see here is the apply pressure, inner pressure of the fingertip here. So in on of the case, you can see that you can grasp the object with less inner pressure. Okay, so we also try to apply this into the robotics system, and So you can see the difference between the microstructure part and the normal part like that. So in so most of the case, the microstructure parts can grasp the object with less force and also more stable compared to the normal part. Okay, so another question is, okay, so how about when you change, when you grasp from the inside the liquid, right? So, okay. So in this case, so our developed one can also perform a bit better compared to the with the normal part. This is the soy sauce, and we also try with the another kind of solution, which is I think is a sugar solution. Okay, so we also try to change the design of the square. In this case, only to change the width of the groove of the channel, right? With different scale in micrometer. And so we found that, so okay, first compared to the normal part without any structures. So the blues indicate the failure and the red indicate the success. And we try to 10 times, and we count the successful times, and you can see that for the microstructure part, it was quite well. But of course, in with different structures of the micro parts, we also quite different one to each other. So some is very good for specific food object, and some is not. It's like that. Okay, and so before that, try to show this. Okay, so for example, so in the tofu, we found that the width of 15 micrometers actually outperformed the other one. But for the other case, let me see. For another case, it's a very soft object. So actually the width of 22 micrometer is actually outperformed compared to the other ones. On the case, it worked okay, but we also compare the grasping pressure as well. So, and then we found that there's some difference among them. Okay, so so the conclusion here, here is that if you change the morphological design and also the tribological characteristic of your finger, so you can expect to create some you get enhancements in grasping many kind of objects. For example, some very difficult to handle objects like food or deformable, fragile objects like this. And with that, so I would like to conclude my talk. So, and this is I would like to thanks to our team and also our funding agencies. And that's all. So if you have questions, feel free to ask. Thank you.